Hi, I'm Mark Barsamian. In this video, I'll be discussing finding the derivatives of 1 over x and square root of x type functions using the definition of the derivative. This material is from section 2.4 of the book. More specifically, it's from the middle of page 138 to the middle of page 140, examples 6 and 7. And the corresponding homework is 2.4, number 35, 37. Recall from section 2.4 of the book and from the previous video the definition of the derivative. The symbol is that, spoken f prime of x. It's also spoken the derivative of f of x, and it means the function given by this formula. What's this used for? Well, note that, again, this is a function, has a variable x inside. But when you actually substitute a number a in those spots, you get a number f prime parentheses a. And this number can be interpreted as the slope of a tangent line, or also called the slope of the graph. Can be interpreted as the instantaneous rate of change of f of x at that x equals a. If f is a position function for a moving object, then the number f prime parentheses a is the velocity of the moving object at time x equals a. And recall the outline of a process for computing the derivative. I discussed this in the previous video. I discussed that the book has something called a four-step process for finding f prime using the definition of the derivative. I discussed in the previous video that I don't really like their process because it obscures the most important steps. I presented my own version of a process. I decided to instead use the book's four-step process, but just improve it a bit. So here are the steps of the book's four-step process: step 1, 2, 3, 4. But you can see that I've added some stuff to that process. So for instance, you start by presenting the goal very clearly, and you explain very clearly things about the process. So it's a mixture of the book's four-step process and the process that I discussed in the previous video. We'll do two examples today. They're both long examples. The first example is this function f of x equals 7 plus 13 over x. So this is what I would call a 1 over x type function. So our job is to do these 6 things. Find f prime using the definition of the derivative, and then find a bunch of function and derivative values, and then finally illustrate those results on a given graph. Okay, here we go. Let's refer back to our four-step process. We want to present the goal. So our step 1 is to find f of x plus h. Remember how we do that. We write down f of x, then we write down the empty version, and then we plug in x plus h. So there is our f of x plus h. That expression is going to be substituted in that spot later. Now let's go on to step 2. So there's our f of x plus h minus f of x. Now we should simplify this. Notice the 7's cancel just by arithmetic. Now we're faced with subtraction of two fractions that have different denominators, so we have to get a common denominator. Now we just combine these two fractions and simplify. All right. right, there's our f of x plus h minus f of x. There is our f of x plus h minus f of x over h. Now I find fractions divided by something to be confusing. I find it much clearer, instead of dividing by h, to multiply by 1 over h. And there's our f of x plus h minus f of x over h. Now, I don't go any farther in this step. I don't cancel the h over h because we don't know anything about h in this expression. Later in step 4, we will know something about h, and I will cancel h there. I'll point out that in the book's similar example, they do cancel the h's in this step 3. I don't find that as clear as it should be, so I don't cancel the h's here in step 3. Now let's go on to step 4. So there we've substituted in our result from step 3, our f of x plus h minus f of x over h. Now, I have not been doing something that I mentioned in the 4-step process. I mentioned in the 4-step process that we should point out limits that are indeterminate forms. Notice that this is an indeterminate form because of the h over h. And in the very first step, the original limit was an indeterminate form. Because if you substitute in h equals 0 into that original limit, you'll get 0 over 0. And remember what I mentioned in a previous video, limits of these difference quotients are always indeterminate forms. But remember, we know something about h. We know that h is approaching 0, so h is not 0, so we can cancel the h over h. That's that most important step of the first month of the course. Now we have to be very clear and show the result of that cancellation. Notice that that is no longer an indeterminate form. In fact, that's a rational function with variable h. Why did I say the variable is h, not x? Well, because the h is the thing that is varying. Now, notice about that rational function, if I substitute in h equals 0, nothing goes wrong. In other words, h equals 0 is in the domain of that rational function. So theorem 3 tells us that we can just substitute in h equals 0. And there's our result. We found that f prime of x equals minus 13 over x squared. So I'm going to write a little summary over to the side. Notice a couple more things about this 4th step. Notice that in all of these lines at the beginning, there was a limit sitting in front of the expression. We had not done the limit yet. We are not able to do the limit in these first couple of lines because we had an indeterminate form. And so we substituted in the rewritten form of the expression, and then we used what we knew about h to cancel the h over h, and then we arrived at this limit, which was no longer an indeterminate form. And then once we use theorem 3, we end up with an expression that does not have a limit expression in the front of it. The limit symbol goes away when you use theorem 3. That's the end of part A. Now let's go on to part B. In part B, we're supposed to find f of 1 and f prime of 1. Well, remember our formulas. There's our result for part B. Part C, we're supposed to do the same thing, but with x equals 2. Now let's go on to part D. And then on to part E. Finally, let's go on to part F, which is to illustrate these using a given graph. So there's a given graph of f of x equals 7 plus 13 over x. So we need to illustrate our results. Well, let's go back and review our results. In part B, we found that f of 1 is 14 and f prime of 1 equals minus 13. So this tells us that there will be a point on the graph at 1, 14. And this result tells us that the slope of the tangent line at x equals 1 is m equals negative 13. So let's go down and add those features to the graph. I made a mistake here. This should not be the number 14. This should be the number 20. And this should be the number 20 as well. Go down and add those features to the graph. So there's our point with coordinates 1, 20. And we have to draw a tangent line and indicate that its slope is m equals negative 13. Now let's go back up and see our results from part C. In part C, we found that f of 2 is 27 halves and f prime of 2 is minus 13 fourths. So there's a point on the graph at 2, 27 halves. And the slope of the graph is minus 13 fourths. So let's go down and add those features to the graph. So there's our point at 2, 27 halves. Remember, 27 halves is 13 and a half, so that's about the right location. And then we need to add a tangent line and indicate its slope. Now let's go back up and see our results from D. In D, we found that, which tells us that there's a point at 1/2, 33. And there's this result, which tells us that the tangent line slope is negative 52. Let's add those features to the graph. So there's the point with coordinates 1/2, 33. And the tangent line has slope negative 52. Notice those numbers that we got for those slopes agree with the graph. The graph is steep here and not steep here, or not as steep. Finally, let's add our result from part E. In part E, we found this, which tells us that there's a point at negative 2, 1/2. And this derivative result tells us the slope of the tangent line. Let's add those features to the graph. All right, so there's our point. Notice that if we had just looked at this computer graph without having the information from our computations, we would have maybe thought that there was an x-intercept at x equals 2. But we realize, no, at x equals negative 2, the graph is slightly above the x-axis. The x-intercept happens in here somewhere, not at x equals negative 2. All right, so there's our point. Now we have to draw the tangent line and indicate its slope. Notice something interesting here. At x equals -2 and x equals +2, the slope of the tangent line is -13/4. So those two tangent lines are actually parallel. The y values are different at those two x values, so those two tangent lines are parallel, they don't touch, but they do have the same slope. All right, that's the end of example 1. Let's go on to example 2. Example 2 is the exact same kind of problem, except this time the function is f of x equals 7 plus 13 square root of x. The previous problem, the function was 7 plus 13 over x. So this is what I call a square root type function. All right, well, our problem will unfold the same way. Let's find f prime using the definition of the derivative. We'll use the four-step process with my additional explanations. So we start by writing down what we are going to be finding. Now step 1. So we took the same approach that we took in previous problems. We found f of x plus h by starting with f of x, building the empty version. So it's clear how to construct f of x plus h. You substitute in x plus h into all of those empty parentheses. Now let's go on and do step 2. Notice here it's very important to include these parentheses. If you don't include these parentheses, the next step will be wrong. Now notice that the 7's cancel. And that leaves us with the following expression. Now I'm going to factor out a 13 to make the calculations easier. Now we have a step that is a trick step. We're going to multiply and divide by a special term. The special term we're going to get by scrutinizing this expression. We have a square root of something minus square root of something. The term that we're going to multiply and divide by is going to be similar to that, but it's going to be square root plus square root. So again, we noticed that we had a minus sign in this expression, so we built this special term with plus signs there. Now we just multiply out the numerator. We don't do anything with the denominator. We just multiply all the numerator terms together. And notice that there are two terms that are identical but have opposite signs. This term and this term cancel because they have opposite signs. That sign should be clear. That should be a plus sign. So cancel those terms using arithmetic. Furthermore, these terms here can be simplified. Square root of x plus h times square root of x plus h is just x plus h. Square root of x times square root of x is just square root of x. So when we simplify the red terms, that circled red term just becomes x plus h. And that circled red term just becomes x. Now we can do some more canceling. These x's cancel. And there's our result. We have found that this expression, f of x plus h minus f of x, is this messy thing. Now let's go on to step 3. Now here, I want to note that the result that we got in the previous step was a fraction. Our result was a fraction. In the current step, we're being asked to divide that fraction by h. Well, as in the previous problem, it's clearer, makes the presentation on the page clearer if instead of writing this as dividing by h, we write it as multiplying by 1 over h. Now we go back and get our results from the previous step. This circled expression is going to be put in for f of x plus h minus f of x. So there's our expression for f of x plus h minus f of x over h. Finally, in step 4, we build the expression for f prime and compute it. So there we've used the result from step 3. And here we should note that this limit is an indeterminate form. And of course, the original limit was also an indeterminate form. But realize that the reason that it's indeterminate is the h over h. And we can do something about that. We know something about h. So we show very clearly the result of the cancellation. Remember, that's the most important step of the first month of the course, so you want to show the before and the after of canceling. Now, this expression that we've got, that we have to take the limit of, is not a rational function, but it is a function made up of basic functions, and the gist of it is that if you substitute in h equals 0, nothing goes wrong. So we're not using theorem 3, but we're using something like theorem 3. Basically, if you have a function that is continuous at your x value, then you can find the limit by just substituting in the x value. So we just substitute in h equals 0. Now this is a little confusing because on one line above we said h is not 0. Now we're saying h is 0. That might be confusing. The idea is that once we cancel the h over h and we arrive at this limit, we don't have to worry about how we got here. We know that we're being asked to find the limit of some expression. Now we can use facts about limits to find the limit of that expression. When I substitute in h equals 0, I end up with this simpler expression. Notice that the limit in front is no longer there. When I substitute in my x value, I've done the limit. Now I'm just simplifying. So there's our result. We found that f prime of x is this thing. Let's write a summary of this on the next page. So here's our summary. Now let's compute our function values and derivative values in parts B, C, D, and E. So f of 1 is 14, which tells us that there's a point on the graph at 1, 14. Now find f prime of 1. The result was f prime of 1 is 13 halves. That tells us that the tangent line at x equals 1 has slope, m equals 13 halves. Now let's go on to part C. So f of 4 is the number 33. That tells us there's a point on the graph at 4, 33. Now let's find f prime, parentheses 4. So f prime of 4 is 13/4. That tells us the tangent line has slope. M equals 13/4. Part D, do the same thing at x equals 1/4. F of 1/4 is the number 27 halves. That tells us there's a point on the graph at 7, 27 halves. F prime of 1/4 is 13. That tells us the tangent line slope at x equals 1/4 is the number m equals 13. Finally, question D. Do the same stuff at x equals 0. So we found that f of 0 is the number 7. That tells us that there's a point on the graph at 0, 7. I see that I wrote down a wacky thing in part D. Part D, the x-coordinate is not 7, it's 1/4. So this should say point at 1/4, 27 halves. Finally, for the last part of part E, we have to find f prime parentheses 0. All right, well, we have a strange result. F prime parentheses 0 does not exist. I'm not sure what that is going to tell us. We'll have to go down and look at the graph. There's the graph of f of x equals 7 plus 13 square root of x. So let's illustrate our results from parts B, C, D, and E. In part B, we found that when x is 1, y is 14. So there's a point 1, 14. And we found that f prime parentheses 1 was 13 halves. That told us that this tangent line has slope m equals 13 halves. In part C, we found that f of 4 was 33, and we found that f prime parentheses 4 was 13/4. So those things told us about a point on the graph at 4, 33, and a tangent line slope there of m equals 13/4. So let's add those to the graph. Okay, let's go back up and look at our results from part D. In part D, we determined that f of 1/4 was this number 27 halves. That told us about a point on the graph at 1/4, 27 halves. We found that f prime parentheses 1/4 is 13. That told us that the tangent line slope there was the number m equals 13. So let's go down and add that information to the graph. Now look at those 3 points. Notice that as we go to the right, the y values get larger, but the slopes get smaller. The slopes get closer to 0. That is, this is the steepest tangent line. This is the least steep tangent line. Now let's add our results to part E to this graph. In part E, we found that f of 0 was the number 7. So there's a y-intercept at 0, 7. But we found that f prime parentheses 0 does not exist. What's up with that? Well, first of all, let's plot the point 0, 7. And then let's look very carefully at this graph. If we had to draw a tangent line on this graph, it would look like this. We actually haven't discussed this situation before. The tangent line for this graph at x equals 0 would be a vertical line. And vertical lines have undefined slope. Remember that the value of the derivative is the number that's the slope of the tangent line. If the tangent line is vertical, then there is no number that's the tangent line slope, so there is no number that's the value of the derivative. Now, why do we know that this tangent line is vertical? Well, remember that the square root function can be obtained by starting with a parabola and flipping it. So if we had y equals x squared, its tangent line at the point 0, 0 is a horizontal tangent line. When we flip this on its side, we get the graph x equals y squared. This graph has a vertical tangent line at that point. Now, the graph of y equals square root of x is the upper arm of that graph. We see that this y equals square root of x has a vertical tangent at x equals 0, and that's why it makes sense that f prime parentheses 0 does not exist. That's the end of this example. That's the end of the video. Thank you.